Did you know all you need to generate energy, or to generate electricity, in our case to generate a current, is a magnet and a coil of wire. You can't see here, but inside here you've got a coil of wire all along the ground. And all you need to do is move a magnet in and out of a coil and you generate electricity. There's no way to see we're generating electricity here, so even though I keep doing this, it doesn't look like I'm generating electricity, but I actually am. So to prove it to you, I'm going to hook this up to what's known as a galvanometer, which is a bit like an ammeter, and basically it measures current. And now as I move this in and out, lo and behold, my dial is moving, telling me that I am generating electricity. So almost all the electricity that you've got in your home is generated somewhere along the line by a magnet moving in and out of a coil, or maybe I keep the magnet stationary and get a coil moving in and out of a magnet. So every time you plug your kettle in, it's plugging into wires, and the wires somewhere along the line are being connected all the way back to a generating station. And that generating station, somewhere inside of it, has got a big magnet and a big coil of wire, and one of them is turning relative to the other. Okay, so we get rid of the galvanometer just to show you what's going on here. I'm going to turn the, well actually I'll try it like this before I turn the light on. Once again, in and out. And you probably can't pick up on that. Let me just flick it up to there. And we go again.
Yeah.
Yeah, you can actually pick it up.
Mm-hmm.
Okay. Well actually we'll get a little bit more impressive. We're going to turn off the lights. Doesn't matter if I look stupid or sound stupid. This is pretty interesting because every bit of electricity you get at home when you plug something in is coming from a magnet going in and out of a coil of wire. This is an LED, so it only allows the electricity to flow in one direction, so it only happens when I pull out the magnet and not when it's going in. So, or in this case, sorry, it's when it's going in it works, not when it's going out. So all electricity that works in that fashion just needs a coil of wire and a magnet. Basically, in a power station, you've got a primitive version of this. Magnets are on the side, a coil of wire in here, and if I attach two leads to this, all I've got to do is somehow make it turn, attach two leads coming out, and I've got electricity. And that's what they've got in power stations. Now the only difference between a gas-powered power station and a turf and nuclear-powered is they have different ways of making this guy turn. Usually it involves producing steam, so you want to heat something up to produce steam to make this guy turn, and now you've got a coil turning inside the magnet, and you've got electricity coming out. So I always think that's impressive. People think that different power stations are completely different. All they do is they make this guy turn in different ways. And like I said, they all tend to use steam to do it. It's just how they heat the steam is different. Let's look at another variation on that. These are becoming more and more popular, particularly in third world countries where they don't have batteries. All you need, once again, inside here is a coil, which you may or may not be able to pick up on, and inside of that, there's a magnet. And as I move one relative to the other, this again is fairly impressive. I'm going to shut off the lights. So very handy if you don't have electricity. All you need is a magnet and a coil of wire. Now when you stop it, it doesn't work. Now usually these guys have got something inside them called capacitors, which store the charge when you don't need it. So as you're walking along, you could be shaking this. I could have this turned off, so it's storing up all the charge and it only gets released when you want it. Now just like powering a light bulb, you can do something similar to power a radio. In fact, there's a new device being built for hikers such that they can charge. In fact, I won't turn on the lights. Can we now get you, Mark, just to focus? Oh no, we will. No, we won't turn on the lights. We've got something similar here, which is my dynamo. Dynamos, everybody used to have these years ago when we didn't have money for batteries. Once again, this used to be attached to your bicycle. And the bicycle made this turn, and you were turning a magnet inside the magnetic field, and you got the light on your bike shining up. But now we don't bother with those anymore, because now we just buy batteries and we throw the batteries away. Electricity is produced by batteries in a separate fashion. That's chemical. But in this respect, all you need is a magnet and a coil of wire. So we're going to finish up. If you can get the big screen up there, Mark, let me know when you got it. Just by looking at a computer simulation of what's happening here. And on the website, I give you an address for where you can locate this. But once again, what you've got is a magnet and a coil of wire. You're thereabouts. My coil of wire is this here. You can see the electrons in it. It's hooked up to a light bulb. And now, rather than moving the magnet in and out of the coil of wire, we're just going to make the magnet rotate about. And to make the magnet rotate about, we turn on our tap. And as we turn on our tap, we've got a big play down here at the bottom. As we turn on our tap, it makes the wheel move around, which makes the magnet move around, so it's a bit like the magnet is moving in and out of the coil of wire. If I make the magnet move faster by turning on more water, it's going around more quickly, and as a result, my light bulb flashes more quickly. Once again, all you need is a magnet and a coil of wire to generate electricity. The fancy word for it is electromagnetic induction, and it was discovered by Michael Faraday back in 1820.